Um, these mini tab printouts basically give you the results of a correlation regression analysis, just in a somewhat different form than you would be expecting. Right? So it's really just a matter of interpreting what the printout is really trying to tell us. We kind of run into an issue with this because most of the time they don't give you the raw data, so there really is no way around answering a question related to this without knowing what these coefficients represent. All right, so that's what this page is all about. Right, but there are some things that are kind of, I'd say, obvious. Right, like R dash SQ, R squared. It's pretty obvious what that represents. Excuse me. The R squared adjusted is not something we really work with too much, but then you see the regression equation is volume is equal to negative 87.1 plus 1.54 height. All right, it's like, well, okay, so one of them is the input variable, the other is the output variable. I mean, it says regression analysis volume versus height. So if the dependent variable is the one that's solved for, then that it's a reasonable assumption that that's our y hat. All right, so this would be y hat is equal to negative 87.1 plus 1.54 x. All right, so the y hat is taking on the role, or volume's taking on the role of y hat, and height is taking on the role of x. All right, so it's pretty easy once you get that relationship down. All right, the other coefficients start to kind of fall into place. Right, because you see constant, you see height. It's like, oh, what does each one represent? But then you see the relationship between constant and your y-intercept, height and slope. Right, so that's exactly what they represent. All right, so this is our fixed value, or the y-intercept, and this would be our slope. So just being able to read that information gives you the correlation. The coefficients of the regression equation. All right, so you don't really need the raw data because you have everything you need here. All right, you have a standard deviation. We'll get to that in a minute. SE coefficient. I'll get to that in a minute. But you also have the R squared value, so that's giving you the correlation between the two variables. All right. I mean, you got to do a little work with it. You got to take the square root of it in order to get the correlation value, but you have everything you need there. All right. The R squared, again, is the coefficient of determination, but it still gives us a good idea of what the relationship is. All right. The closer the R squared is to 1, the closer it is to perfection. All right. So that's what all of this stuff is really kind of getting at. All right. Everything is detailed there: constant, height, slope, prediction equation. But then you have the SE coefficient. All right. So SE coefficient represents the standard deviation of the slope. All right. So we're looking at a relationship between two variables. That's the slope, the change in y over change in x. So this gives us the standard deviation of that slope, all right, of that change in y over change in x. All right. The S itself gives us the standard deviation of the residuals. I kind of dropped the ball here in terms of consistency with capital lowercase. So everywhere you see an S, it should be a lowercase s. All right, so there's typos galore here. All right, so I mean, I would draw another S as a lowercase, but it's just going to look like an uppercase the way I make them. So every one of those S's should be a lowercase s. All right. So standard deviation of the residuals, you think about what a residual is, that's the difference between the observed and the expected values. All right. So the observed as in what was in the data set, the expected as in what you would get if you took the x value and plugged it into the regression equation. All right. So one is observed, one is predicted or expected. All right. The difference between those two would be a form of deviation. All right. So what S is giving us is the deviation of the deviation. All right. So how far the residuals are away from the average value. All right. So that would be the y bar. The R squared we know about. There is, I mean, I didn't do this on purpose, but so it's not really a typo, although it kind of seems that way. You see in the printout, it's capital R squared, and then in my description, it's lowercase r squared. But that's because of the inconsistency with the formula, because you have certain circumstances where we use a lowercase r squared. So for a linear regression, linear correlation coefficient, linear coefficient of determination, those are lowercase r's, as opposed to other types of nonlinear relationships which are capital R's. Right? So since this is a linear situation, it actually should be in the Minitab printout, it should be a lowercase r squared. But for whatever reason, they don't do that. They give a capital R. So the typo is on every computer system throughout the world that does statistical printouts, assuming that they actually give a capital R. So it really should be lowercase r, but you'll see in most of the printouts they'll give capital R. I don't know why. All right. But we do know that R gives us the strength of a relationship between the two variables. All right. So on the next page, a more detailed breakdown with like arrows drawn and all that good stuff. So, but we'll go right to an example. Write the equation. A question. That's a fun word that I just made up. The equation is what I meant to say. No, write the equation of the regression line. I got equation and regression kind of merged, and all hell broke loose there. So the equation of the regression line, y hat is equal to the constant, so negative 42.734 plus 1.7 x. All right. We don't really work with the t stuff just yet. We'll get to that in the next unit. So when you see t ratio, t value, p value, things like that, we're not going to touch on that until the next unit. All right. Explain, interpret the information provided by the r squared in the context of this problem. So coefficient of determination is the percent of variation in one variable that can be explained by variation in the other variable. So the r square value is 67.8. So what that's saying is 67.8% of the variation in the context of the problem. So we got to go back to the context. Sample of men agreed to participate in a study to determine the relationship between several variables, including height, weight, and waist size and percent body fat. Scatter plot with body fat on the y-axis, so that would be the output, and waist size on the horizontal axis, so that would be the input, revealed a positive linear association between these variables. All right, so 68% of the variation in percent body fat can be explained by variation in waist size. All right. The buzz phrase that you'll see, I think it's on the previous page. Yeah, correlation doesn't imply causation. Right? Just because there's a relationship between two variables doesn't. That was weird. So we look at this and say, can we determine that change in waist size caused a change in percent body fat? It doesn't seem to make sense. I mean, if anything, it would probably be the other way around. But just because you have a correlation between the two variables doesn't mean one actually caused the other to happen. I saw in your recent studies, the activities where you collected data, there were some research questions like, does what's the relationship between hours of sleep and math grade? That was an example. GPA was another example. Yeah, will, if there is a relationship between hours of sleep and math grade, will it be reasonable to say that the number of hours that you get of sleep per night, will that cause a change in your math grade? I mean, there's a case to be made either way, right? So it depends on what you're doing. Let's say you're not getting as much sleep, so you're gaining a couple of hours of time being awake. What are you doing with those couple of hours of time being awake? You know, if it's you studying math, then it could be a causal relationship. But if it's spent doing something else unrelated to math, then there's no reason to think it would be a causal relationship. All right, so it's just stuff to keep in mind, because you could have a perfect correlation, but that doesn't mean one variable caused the other to happen. All right? And that should always be addressed in any conclusion that you write. You should always consider whether one caused the other to happen, and if it didn't, explain why that would be the case. All right. One of the men who participated in the study had waist size 35 inches and 10% body fat. Calculate the residual associated with the point for this individual. All right. So we know the observed value was 10. We need the expected value. So I need y hat of 35. All right, so that would be negative 42.734 plus 1.7 times 35. All right, so get the old calculator out here. $734 plus 1.7 times 35. So this is the expected value, 16.766. What I need to determine is the residual. Nope, that's not a marker. The residual of 35, which is going to be 10 minus 16.766. So negative 6.766. All right. So it's off by almost 7%, but on the low side. All right. It should have been 6.766 percentage points higher. All right. But it came out, computationally with a result of 10. So we want to make sure we get the units. In this case, it's percent, all right, because the resulting variable or the response variable was percent. All right. So, you can see the different pieces of information that you can pull from the table. All right. But in number 2, determine the LSRL, again, least squares regression line. All right, so linear regression equation. Standard deviation for slope. All right. Correlation coefficient and the standard error of the residuals. All right, so it takes a little getting used to. Some parts are pretty easy. Some parts are, not so much. But the least squares regression line should be one of those really easy parts. All right. So I guess I could just write it in here in this little box that I created for some reason. So y hat would be equal to negative 87.12 plus 1.5433x. All right, that's the LSRL. All right, so standard deviation for the slope, you go back to that page that has all the breakdowns on it, but the standard deviation for the slope is SE coefficient. All right, well, which one? You see we have 2 possible SE coefficients. The height represents the slope. So again, this is the y-intercept, and this is my slope. So the one I want, when I talk about the standard deviation for the slope, I want SE for height. All right. Now there are two variables here, are volume versus height. So it's just a question of, all right, well, what, one is going to predict the other. So which one is the explanatory and which one is the response? So it's always a weird question, because it's like we have two variables, one versus the other. If we go back to the previous one, this was percent body fat versus waist size. All right, so the waist size was the explanatory variable, percent body fat was the response variable. All right. And then here we had volume versus height. It's the same data set, but it gave us volume as a result of height. All right. So whatever that predictor value is, that variable, that's going to be your input variable. All right. So height here is my input variable. Waist size is my input variable. Since this is the same one as before, we're talking about height as the input variable. All right. Why does that matter? Because when I'm talking about the units, it's a possibility of height or volume. Those are two different types of units. All right. One's linear and one's cubic. All right. In this case, I'm talking about height. So it would be whatever the linear units are, inches, centimeters. They didn't tell us here, but we would want to make sure we include that in our write-up. So when we say SE height, we would say 0.3839 inches, meters, feet, whatever the units are. All right. So just keep that in mind. Here, again, it doesn't make sense because they didn't tell us, but it will very often be presented to you. All right. So we want to have that information. Standard error of the residuals. All right. So again, back to our little breakdown here. Standard error of the residuals, that's the one that I accidentally capitalized. All right. So the S value, standard deviation, that's the weird one. It's the deviation of the deviation. All right, because residual is the difference between the y and the y hat. So this is the standard deviation of that. So S would be equal to 13.4. All right. So math versus essays. I think I answered every part of the question. Yeah. So, like essays as a qualitative thing, or what are we talking about? Like the grade on an essay? They didn't tell us, so we just do our best. It could be the number of essays written, length of an essay, who knows, So just keep that in mind when you're thinking about units. So we're talking about 27.57 plus 0.6548x. All right. So SE essays I omitted the correlation coefficient on the last one. I'll get to that in a minute. But SE essays would be 0.3154. And again, what are the units? Who knows? All right. So we're not going to write anything, but we do know that we'd have to include those. All right. S, standard error of the residuals. So 9.140. But again, the correlation coefficient R is the square root of R squared. So the square root of 0.35. We'd have to go with an estimate here. And that's fine. That's all we can do. All right, so about 0.592. All right, so going back to the previous one, R would be the square root of 0.358. All right, so second enter. So about 0.598. All right, so again, it's not terrible. It's just you got to know what each of the things represent, and a lot of it's irrelevant, So when we look at this, it was like, unless they specifically asked us for the standard error of the coefficient, we wouldn't consider the 29.27. and we're not going to bother with the t or the p values. All right, so we don't really have to know too much of the table just yet, but the important stuff, obviously. All right, so that's it for the unit.